Hi everyone, welcome to G World of Academic Physics. Today we will discuss some more application of electric flux. Continuing that electric flux applications, we will add some more applications to improve the ability of a student. This is also a very basic applications I am taking. This is a non-conducting disk. Exactly on the axis of the non-conducting disk, a infinite line charge having line charge density lambda is connected like this, and the radius of this disk is r. And the question is asking how much flux will passes through this disk due to this infinite line charge having line charge density lambda. We know that this disk is an extended body. When this kind of questions are asked to us, we must think about an element. So in this case, we will consider an elementary ring, because disk is combination of so many infinite number of rings. So I will consider one elementary ring, and this radius of this elementary ring is r and the thickness is dr. So I want to draw it here again. This is my elementary ring whose radius is r and thickness of this elementary ring is dr, and one line charge is connected here, this elementary ring having line charge density lambda. A student must have the informations. If the line charge one end goes to infinity, if you observe this one, it is goes to infinity, this one end goes to infinity. So for one end goes to infinity, the expression of electric field at certain distance r having two components of electric field. One is perpendicular component, another one is parallel component. The perpendicular component is k lambda by r and the parallel component also k lambda by r. So exactly the same fashion, here two components of electric field, one is k lambda by r, another one also k lambda by r. This is the preliminary informations that student has to be in the mind. So how many components? Two component. One is k lambda by r perpendicular, another one is k lambda by r. If you observe very carefully these sections, the perpendicular component here it is k lambda by r. If I will consider this side, it is also k lambda by r, and here it will be, this is small r, I must include small r. This section it is also k lambda by r, this section it is also k lambda by r. A student has to be imagine that this section it goes upward, this section it is downward, that side it goes like this, that side also it is goes like this. So what will happen? The net electric field only in the horizontal directions, that is k lambda by r. And what is that electric field direction is which direction? That is k lambda by r. The rest perpendicular components have cancelled each other. So what will happen? I will write my elementary flux. The elementary flux is d phi. It can be written as E dot dA. That is my basic definition. The area vector also like this. So what is E? That is k lambda by r. And what is dA? I will write the elementary area, that is 2 pi r dr. And what is the angle between E and dA? The angle is nothing but cos 0 degree, and I will simply integrate. What is the expression is coming? This is lambda, and what is the value of k? 4 pi epsilon naught into 2 pi r cancelled, and simply the integration of dr, and cos 0 is 1. So integrating this dr, the limit is, if I will consider my element is here, this is dr. If I will consider my bigger disk, little more bigger ring, then the element is dr. dr, if I will add up like this, I will get total integration limit is 0 to r. Proceeding in the similar fashion, the expression is coming 2 epsilon naught, and this integration solve will get this result, that is lambda r upon 2 epsilon naught. This is my final answer. Let me one more time to explain my student. This is a non-conducting disk. Exactly on the axis of the disk, a infinite line charge, one end goes to infinitive line charge as connected. The question is asking, due to this infinite line charge, how much flux is passes through this disk. We know that disk, the ring is an element in case of a disk. So we will consider a ring of radius r and thickness of this ring is dr. And we know that if one end goes to infinity, the expression of electric field is having two components of electric field. One is k lambda by r perpendicular component, another one is k lambda by r horizontal component. So simply I will write k lambda by r perpendicular component and this is k lambda by r horizontal component. But if you observe very carefully, this k lambda by r upward symmetrically it is also downward in these sections. Also this side it goes like this and that side also it goes like this. So what will happen? The net electric field only in the horizontal direction, that is k lambda by r, and area vector is perpendicular to the plane and it is also along the direction of electric field. So angle between electric field and area vector it is 0 degree because both are parallel to each other, and I will write my elementary flux, I will write my elementary area, and proceeding in the similar fashion going for the integration I will get the conclusion that lambda r upon 2 epsilon naught. I hope this question is pretty clear to everyone. Let me draw one more application of electric flux. This is a very similar questions already in the competitive exams. This is a line charge, infinite line charge. This is infinite line charge. This end goes to infinity and this end also goes to infinity. Exactly at a certain distance d, there will be a rectangular sheet. These questions came in the JEE paper. Rectangular sheet, and this rectangular sheet having some distance d and length is L and breadth is B. I hope this scenario is clear to everyone. The question is asking how much flux will passes through this rectangular sheet due to this infinitely line charge. I hope the scenario is pretty clear. One more time I want to repeat for the student perspective. This is a infinite line charge. Exactly at a certain distance d, a rectangular non-conducting sheet have placed here, and question is asking how much flux will passes through this rectangular sheet. If you observe very carefully these sections, this rectangular sheet I will consider one elements on this rectangular sheet. So exactly I will draw a section, mid sections, and from these mid sections, from distance x, I will consider one element of this rectangular sheet. How to approach this kind of question? X to dx, one element I have considered this. So if I will redraw this scenario here, the top view I want to draw, this is my infinite line charge. Exactly at a distance d, the scenario is like this. I will consider one small element here at a distance x, and the element I connect like this. The element thickness is dx. This thickness is dx and it is exactly like this. This element is exactly like this. I hope the visualization is pretty clear, and this is subtended an angle theta. If you observe very carefully, this is d, this is x, and this distance is nothing but d square plus x square using the simple Pythagoras theorem. This is d square plus x square like this, and the electric field is going like this, and the area vector is like this. This angle theta, so this angle also theta. Here if I want to draw like this, the electric field will be go like this and the area vector is like this. This angle is theta. I hope the visualization is pretty clear to everyone. So if I will write my elementary flux, I will write my d phi, and this is nothing but E dot dA, and phi is nothing but integration of E dot dA. This is my expression of elementary flux. I will go for the net flux, I will simply integrate. What is the expression of electric field due to infinitely line charge exactly at a distance d? This is very clear that student has to be in the mind. If it is an infinitely line charge, this is goes infinity, this end goes to infinity. Exactly at certain distance d, the expression of electric field at point P is nothing but 2k lambda by d, and direction is perpendicular to the plane. Direction is perpendicular to this infinite line charge. I hope this scenario is pretty clear to you. Using the same concept here, I'll write my expression of electric field. The electric field is nothing but 2k lambda by d. D is which distance? This distance. D is which distance? This distance. In this case, this is the distance. I'll look this distance, which is nothing but what? D square plus x square root over dA. I'll write the area. The area is nothing but length into breadth, and if you consider this kind of element, if the element is like this, the thickness is dx and length is L, so definitely the length, it will be L dx, the area. And what is the angle between them? Cos theta. Cos theta I will write like this. I will do the integration symbol. This little very carefully, if we will proceed like this, this is 2k lambda upon d square plus x square root over, this is L dx, and I will write cos theta. Look at this here, cos theta is nothing but d upon these things. This is nothing but d upon d square plus x square root over, and this is my integrations. Proceeding in the little similar fashion, this is 2k lambda L d, and this is nothing but integration of dx upon x square plus d square. I hope the scenario is pretty clear. And what is the limit of the integrations? If a student is very carefully in this side, if I will go this sections, this is minus b by 2. If I will go this section, this is plus b by 2. If I will consider this is my origin, I will go this side, it is minus b by 2, and I will go this side, this is plus b by 2, because here also I will consider one element, and the element again I will consider the symmetrically, I will follow like this. So similarly here I will consider one element, I will follow like this. So here I will go minus b by 2, here I will go plus b by 2. So minus b by 2 to plus b by 2, this is my limit of integration. Solving these integrations, this is dx upon a square plus x square root over, this is nothing but 1 by a tan inverse x by a. So I will just write here. So this is 2, k value is 4 pi epsilon naught, this is lambda L and d, and I will write what? 1 by a, here a is d, tan inverse x by a. X is what? This is x by a is what? Your d, and we will put the limit of what? Minus b by 2 to plus b by 2. I hope the scenario is clear to everyone. Just this is nothing but what? This is 2. This 2 has cancelled, and will similar fashion we are moving like this. So 2, this is lambda L upon pi epsilon naught, this is d and d, this have cancelled, and this is tan inverse x by d, tan inverse x by d. So this is nothing but tan inverse x is what? B by 2d, and minus of tan inverse of minus b by 2d, that is giving rise to minus. This minus is nothing but plus. So we will get the expressions that lambda by L, here also 1 2 is there because 2 cancel, 2 pi epsilon naught, this is 2 tan inverse b by 2d. 2 have cancelled. So my final result is coming what? That is lambda L upon pi epsilon naught, this is tan inverse b by 2d. I hope the expression is pretty clear, the expression of the flux. One more time I want to repeat for the student perspectives. This is an infinite line charge. Exactly at a certain distance d, a rectangular sheet of length L and breadth V is placed. The question is asking how much flux is passes through this non-conducting rectangular sheet. I will consider one small element here. From x to dx, I consider one element, and I will write the expression of my flux, that is E dot dA. What is the expression of electric field due to an infinitely line charge? The expression is 2k lambda by r or 2k lambda by d. But which distance I will prefer? This is the distance I will write because I am writing for this element. So expression is 2k lambda by this distance. So I will write my this distance. The area is what? Length into breadth. Length is L, thickness is dx. I will write my area, elementary area, and cos theta. Putting the value of cos theta, doing the basic integration skills, I reached to the conclusion that phi the flux phi is nothing but lambda L upon pi epsilon naught tan inverse B by D. These questions can be solved in another way. How these questions can be solved in another way? I want to draw here. This is my line charge. This is using the concept of Gauss law we can do. This is my line charge. This is infinitely line charge. I will construct an cylinder because I want to enclose this charge. So this is definitely a cylinder I will make to enclose this charge. This is an infinite cylinder. Exactly, this is my seat. How this seat has made here? This is my seat. And the scenario is like this. This seat exactly at some distance D, and the length is L, and this duri is B. I hope this is can be drawn. Student can be think like this. If you want to enclosed, you have to be think like this. This is D, this is length and breadth. And if you one can observe, for a line charge, the field lines will be like this. The line charge, the field lines will be like this, and it is lies in a plane. It is lies in a plane. So definitely the field lines will move in a circle like this. The field lines will move in a circle. So definitely the angle that field lines cover, that is nothing but the 2 pi angles it will cover. And we know if a charge is enclosed within a closed surface, the flux is nothing but q upon epsilon naught. So in this case, if I will write the same statement, for 2 pi solid angle, the flux is nothing but q upon epsilon naught. That is, q can be written as in term of line charge density, that is lambda L upon epsilon naught. 2 pi solid angle, the flux is nothing but lambda L upon epsilon naught. One solid angle, the flux is lambda upon 2 pi epsilon naught. This much of flux due to one solid angle formed. How much solid angle it will construct here? I want this angle. I want which angle? This angle I want. If this is my D and this is total is B, half I can say this is B by 2. I hope the scenario is clear to everyone. This is D, this half is B by 2, and I said this angle is theta. Little redraw to it a better views. This is kind of scenario. It is like this. I will consider this angle as theta. So this is B by 2, this is D. If I will write my tan theta is nothing but B by 2D. So how much tan theta? Theta equals to nothing but tan inverse B by 2D. I will get the theta value. But how much theta? 2 theta I needed because this angle I were looking for. So 2 theta is nothing but 2 tan inverse B by 2D. So it is pretty clear that how much angle, this angle is how much? This angle is nothing but 2 tan inverse B by 2D. So 2 pi solid angle, the charge is q by epsilon naught. 1 solid angle, the charge is nothing but lambda L upon epsilon naught. 1 solid angle get these things. And this much of this much of angle, what I will say? 2 pi angles, this is q by epsilon naught. 2 pi lambda L upon epsilon naught. 1 angle, how much flux? In 1 angle, this much of flux. And this angle, how much flux? If someone will ask you, into what? 2 tan inverse B by 2D. So 2 have cancelled. This is lambda L upon pi epsilon naught. This is tan inverse B by 2D. Little here I will correct my language. This is not solid angle. I just want to say, in 2 pi angle, the flux is q by epsilon naught. Make it correct, that not solid angle. This is 2 pi angle. How much flux is passed? This cylinder, that is q by epsilon naught. This is lambda L upon epsilon naught. 1 angle, how much? In this angle, how much flux will be passed? I will multiply into that angle. I will directly get the expressions. If a student is pretty aware, student can predict this kind of question through this method also. The basic is integration skills, and one can use the short method to approach of these questions. And please don't call it to be a solid angle. I will only just to make a student perspective one more time to explain these questions. I will say if a line charge is enclosed within a closed surface, I will imagine like a cylinder. What I will imagine? It's a cylinder. And I will think in cylinder, the electric field lines will be passes in a plane. It's like it passes through the circles like this. Everywhere it will be go like this. So this the angles of it will construct, that is be 2 pi angle, and how much flux, that is q by epsilon naught. Charge can be written as lambda into L. So 2 pi angle, this is lambda L upon epsilon naught. 1 pi angle, it will be lambda L upon epsilon naught upon 2 pi. So we'll get these expressions. And in this angle, how much flux will be passed? I'll simply multiply this angle. This is a normal geometry, a student has to think about it, this basic geometry. I hope the scenario is pretty clear to everyone. Those are looking for this, I hope they understood these things. Those have little good skill, they can think about also. Otherwise, a basic integrations method can be used also. Little do one more application of the electric flux. That will be, the scenario will be think about this. So this is kind of sheet. Exactly, I will construct one more kind of thing I will draw. This is, and this will be things I connected like this. You can see this is a kind of a sheet, rectangular sheet have been folded, partly it has folded like scenario, and I said the uniform electric field has supplied like this. This is an uniform electric field has passed like this. This is the scenario, and this is my E, uniform field. I'll say this is uniform field, electric field. This is uniform electric field. And the question is similar, that how much flux is entering through this curved surface. The curved surface, how much flux is entering? How much flux is entering through this curved surface? How to approach this kind of questions? This is pretty normal question, and I said the height is, this is length is L, and this much of length I will prefer. This cylinder, if it is in a curved surface, I said the length is L. This length is L. When this kind of questions are asked, we will first go for the basic approach, that elementary methods. So I will construct one element here. So very carefully, this is my direction of electric field. I will construct one element here. This element, I will say the length is dx. From theta to d theta, I will consider one element. This is very basic approach. Every cases we are doing like this in ring cases. From theta to d theta, I will consider one element, and this dx, and the radius of this ring is shape is r. So dx can be written as r d theta. This is basic geometry. A student has to be think like this. This is d theta, this is r, and this is dx. So this kind of scenario will be think dx can be written as r d theta. So area vector will be like this. Electric field will be like this. This angle is theta. If I will write my elementary flux, this is d phi. This is nothing but E dot dA. And phi is nothing but integration of E dot dA. I hope the scenario is pretty clear to everyone. What is the expression of electric field? Electric field is uniform, so that's why E. Area I will write. What is my area? Area is nothing but length into thickness. This is my length. This is my length, and this is my thickness. This is my dx, and this is my length. So I will write my length as L, dx is nothing but dx I already, okay, I will write first dx, and what is the angle? This is cos theta. This is the integration scale, and this is E, L, dx can be written as what? R d theta cos theta. Little better arrangement way if I will write E, L, R outside, this is cos theta d theta, and I will do the integrations. And what is the limit of integrations? If you will go this sections, and there is another section here, theta varies 0 to pi by 2, because theta can vary 0 to pi by 2, because element here to here I can go. This section also 0 to pi by 2, but negative. If you clockwise positive, anti-clockwise negative. So limit of the integration is minus pi by 2 to plus pi by 2. And solving ELR cos theta integration is sin theta, and this is minus pi by 2 to plus pi by 2, will directly get the expression 2ELR. This is nothing but, yes, this is the right answer, the expressions of these things. So one more time I want to make for the student perspective, this is E, this is my area vector, and I will consider one element from theta to d theta. I will consider a dx element. Dx can be written as r d theta, with basic skill of geometry. And this area is nothing but length into thickness. This is my length and this is my thickness. These are my thickness. These are my thickness. So I will already go like this. This thickness already I will write these things, and proceeding in the similar fashion I can reach to this conclusion. If a student think in an alternative way, how the student will think? This is a very alternative way also one student can think like this. It's an alternative way that I want to make for the students. The amount of field lines that enter, the amount of field lines that are entering like this, that amount of field lines will enter through this curved surface. I will simply draw these sections. Whatever the field lines will enter here in these sections, the field lines enter, this was the surface that field lines can emit out. And already that field is constant. So I can directly write this is my area vector, and area, this is length, and I know this is radius is r. So this total is 2r, and this length is L. So what is the area? The area you can say 2r into L. So my area is nothing but 2r into L. Area vector is like this, electric field lines also like this, so same direction they are following. So angle between them is 0 degree. So I will write my flux directly as EA. So E is E, and that is 2RL. A student can suddenly, with the fraction of timing, the expressions is matching to these expressions. I hope this expression can match to these expressions. It is a point of observation the student has to think about, that electric field is not non-uniform, electric field is uniform. That's why this case is more useful if it is the uniform things. And whatever the field is entering, the same thing is coming out of through this kind of setups. And this is nothing but a rectangular sheet. I will go for the area of this rectangular sheet, and I will get the conclusions that yes, this much of flux is passing through this, and will go to the conclusions like this. I hope the scenario is pretty clear to everyone. Let me draw one more application for the student perspective. This is a infinite line charge. I will draw like this. Exactly one cube. The cube is connected like this. This is my cube, and the cube has done like this. A cube has connected like this. We will draw the cube like this. Yes, and some cube is like this. The question is asking how much flux passes through the non-touching surface of the cube. This is a cube have connected like this. The question will pass you how much flux passes through the non-touching faces of the cube, and how much flux passes through this face PQRS. Little better way I want to draw this diagram. So I will construct a cube. I will construct a cube first. This is my cube. Here one line charge has connected like this, and this is an infinitely line charge having line charge density is lambda. The question, how many faces have touched here? How many faces have not touched here? We have to think first. If you observe carefully, this face is touching. I am giving a tick mark to the touching faces. This is a touching face. This face is touching. So this is a touching face. This face also touching, because here touch these things is a touching, and there is a backside another one is there, so touching. This is one face, it is touching. This is one face, it is touching. this face also touched, and there is a back side also, one face is there touching. So 4 faces, 4 plus 2 having 6 faces, this 4 is touched and this is what? Untouched. The question has framed how much flux passes through the untouched face. If you look very carefully, due to this infinite line charge, the fields will be on a plane. The fields always in a plane like this. Confirm? So here the field lines will be like this, and it is the area vector is perpendicular to the plane. So this face, the flux cancel out. Similar fashions, here also field lines will be like this, and this is area vector perpendicular, this face also cancel. Similar fashions, the field lines will be go like this, area vector will be perpendicular. So it is very clear that the faces that have touched, for them flux is 0. For them flux is 0. So we will look about the untouched faces. But we must enclose the charge. This is the preliminary thing a student has to think. And how much cube you necessary to enclose? There will be another 3 cube is necessary to enclose this charge line. So I will construct 4 cubes. Already one is there. So 3 cubes additional is necessary to enclose this line charge. So if 4 cubes enclosed to a infinite line charge, due to 4 cubes, if it is enclosed, the flux is q upon epsilon naught. Q can be written as lambda L, because I said this length is L. Cube of length, I preferred this length is L. So 4 cubes for flux is q upon epsilon naught, that is lambda L upon epsilon naught. 1 cube, how much flux will be passed? That is lambda L upon 4 epsilon naught. This much of flux will be passes. In 1 cube, how much flux will be passed? This lambda L upon 4 epsilon naught flux will be passed. In this flux, the flux, how many touch surfaces? 4 touch surfaces, 2 untouched surfaces. So in touched surfaces, flux will be 0, because area vector is perpendicular to this electric field lines. So only 2 untouched faces. On these 2 faces, how much flux will be plus? That is lambda L upon 4 epsilon naught. In one face, how much flux will be passed? That is lambda L upon 8 epsilon naught. I hope the scenario is pretty clear to everyone. In one phase, how much flux will be passed? This is lambda L upon 8 epsilon naught. This is a very simple concept. You must enclose the charge first. How many cubes? 4 cubes. In 4 cubes, how much flux will be passed? Q by epsilon naught, because charge is enclosed by these 4 cubes. In 1 cube, how much flux will be passed? That is Q by 4 epsilon naught. How many touched? How many untouched? Touched surfaces, no flux will be passed. Only untouched surfaces will look in the flux. 2 faces, how much flux? Q by 4 epsilon naught. 1 faces, Q by 8 epsilon naught flux will be passed. Similar fashion, I want to make one more questions. That is a cube. Exactly, the charge is placed at one of the corner. Charge is placed at one of the corner. The question will ask you, in this phase, how much flux will be passes? Give a name to this phase, P, Q, R. These are the very basic questions. First is, you must enclose the charge. How many phases required to enclose the charge? 8 cubes have been necessary, because this is 4 from the top and bottom. This is 4 cubes below, and above also 4 cubes necessary to enclose this charge, so that charge is exactly at the center, because this is 4 cubes below, and there will be 4 cubes above, so that it must be enclosed. So 8 cubes enclosed the charge. The flux is Q by epsilon naught. 1 cube, how much flux will be passed? Q by 8 epsilon naught. So in this cube, how many flux will be passed? Q by 8 epsilon naught. And we will think about this. In this cube, how many touching faces, how many non-touching faces? If this is charge Q, so this is one touching faces, this is one touching faces, and backside one touching faces. So how many flux is Q by 8 epsilon naught? And how many faces? 3 touched and 3 untouched. Due to touched faces, flux is always 0. So how many untouched faces? So 3 untouched faces. In 3 untouched faces, the flux is q by 8 epsilon naught. In one face, it is q by 24 epsilon naught. I hope the scenario is. In 3 untouched face, the flux is q by 8 epsilon naught, because here it is 0. So only 3 untouched face, the flux is q by 8 epsilon naught. 1 untouched face, the flux is q by 24 epsilon naught. So in this is a untouched phase, how much flux will be passed? This is q by 24 epsilon naught. I hope the scenario is pretty clear to everyone. Always look at the touched and untouched surfaces. Touched surfaces, electric field lines are perpendicular to area vector, so no flux will be passes through this. Only untouched faces, the flux will be passes. And how many untouched face? This much of flux. One untouched face, how much flux will be passed? We will easily can calculate. I hope the scenario is pretty clear to everyone. I hope student will like and subscribe the things and appreciate the things. Thank you everyone.